What's up, you guys? We're gonna do some MIT integrals. But first of all, we're gonna start with MIT 2002, and then we're gonna start with MIT 2006. So let's start with MIT 2002 integrals. So here, this x could literally be moved into the front. So it would just be this integral here, in which I would rather do 1 over x. So I would derive this. Sorry, no, this is already derived. I don't know why I did it that way. It's supposed to be like this. Okay. And then I derive that with the alternating sign. And then x is half x squared, the integral of that. So here, this is going to be squared just by experience. So we left off with x squared, or half, of ln of x minus the integral of, so this is half of x, which is just 1/4 x squared, and then plus c, and that's for this integral. Okay, this one here, if you let u equal square root of x, you'll just get 2 cosine square of u du, which is an integral that I memorized because it comes up way too often. This is u plus, I'm put equal sign there, u plus half sine of 2u. That's already times 2 in there, so with this together, it's this answer. Let me double check that. It looks like it, yeah. So here you just plug in u, so your answer should be square root of x plus a half sine 2 root x plus c. That should be your answer. Cool. Alright, and that's 2002 integrals. Let's start with the 2006. So 2006 is much harder, much difficult actually, I would say. So here, I'm, like I said in the video, I'm just trying speed integrating these integrals. I wouldn't consider myself a professional speed integrator, more of just like an average, I guess you can say. Okay. So this one is ugly. Right off the back, it's x squared minus 2. And then it has these nasty polynomials. X squared plus 4, x squared plus 1, then inverse tangent. X squared plus 2 divided by x. It doesn't stop there. Wow. Okay, well, good grief. What? Okay. So, So the first thing is I'm gonna experiment, because that's literally what all scientists do. So I want to find the derivative of inverse tangent of this. The thing is, this is nasty. So because inverse tangent of u is 1 plus u squared plus 1, that's just reference. And then u squared, that's x squared plus 2 all over x square plus 1. And then here, this is multiplied by the derivative. Oh, but that's so disgusting. Okay, well, we don't have a choice. Or do we? Wait a minute. Let's do this bottom part actually. Hold on. I'm curious. What does this part equal? Because that looks respecting to this. So this is going to be what? X4 plus 4x squared plus 4 divided by x squared plus 1. And we get it doesn't really match. What is this when you... This is plus 5x squared plus 4? Why? Well, I guess if you add x squared here, then yeah, that would be it. And that x squared goes on top, I guess. Huh. So I'm going to do a pattern guessing. I'm going to assume that the derivative of this, this, is equal to this. So just by pattern guessing, I'm just going to say let u equal this, and then the derivative is this entire thing. Now again, I'm only guessing, so this is pattern guessing. So I'm going to go 1 over u du, which is equal to the ln of inverse tangent of x squared plus 2 divided by x. Oops, absolute value plus c, which is like really glitched in there. And that would just be my guess. I don't know. I'm actually very curious myself if that is actually the correct answer, because I guessed by following the pattern. So if I plug it in, oh no, why would you do that? My goodness. There you go. Okay. So yeah, it is correct. Cool. There you go. That's my secret integration bee trick. Alright, so, well, not really a perfect secret because it's pattern guessing and you don't know if it's the correct answer or not. So it's like it's a risk. Alright, time to do 2007 integrals. These are qualifying integrals, not regular rounds. So we'll start with this one. No, I'm just gonna do it like this because I'm lazy. Okay, so there is 1 minus e to the power of negative x. I'm going to rewrite this integral. So first of all, I'm going to multiply both top and bottom by e to the x. So I will get e to the x minus 1 e to the x dx. Just like that. Okay. And then at this point, this is just obvious u sub. So this is just ln of e to the x minus 1. And then we have these values, which I hate. Actually, I hate definite integrals in general. Okay. So if we plug in this to here, you get wait. Okay, so this is ln of e of, so this minus 1. So this is just e squared minus e. E squared minus e minus the ln of e minus 1. This is e minus 1. Oh my god. Okay, well, if you split this up, it would become like ln of e plus ln of e, oh, yeah, minus 1. Ln of e minus 1. Yeah, and then these two will cancel out. And then you, so this is just 1. Great. Nice. Cool. Okay. Tangent 6. So here, the first thing that I'm gonna do is I'm gonna separate tan 6x to tan 4x times tan square. So it would look like this. And then, so it's this times tangent square. And I'm going to turn this tangent square into a secant square minus 1. And as you can see, I can already hate this integral because it's one of those chain thingamajigs. So if you could do this very quickly, geez. So this times this is a u sub. So this would be 1/5 tangent 5x, and then minus the integral tan 4x, which we have here, minus 1/3. If you can see the pattern, there's a pattern, because, you know, tangent square secant square x, and then minus this itself. I know I'm going fast, but yeah, I'm just here. You know what? I'll just rewrite this as this. Oh no, sorry. This is 2. Okay. So tangent 4x into tan square times secant square minus 1, and then this becomes this, and then we have tangent square, positive tangent square. So the integral of positive tangent square, this one is an integral to memorize. This is just the integral of tangent square is just tangent x minus x plus c. Okay. Okay. Next one is this integral here. As you can see, I want to factor out the 2. If I am doing this wrong, please let me know in the comments. Okay. 1 over root 2. Alright. And this is just 1 over root 2 inverse sine plus c. Okay. Here, I'm just going to put the answer right here. If you see this, or anything like that, and then you see like a tower of e's, or whatever, the answer is always the highest. And then you just put plus c. So in this case, here, the answer is just e to the x plus c. Okay. It's a very, very common integral. Alright, so this one, integration by parts. You let the ln be derived, and you let the monomial be integrated. So here, when we derive this, this becomes negative 1 over, well, it's, the derivative is 1 over x, but in integration by parts, there's it alternates the sign. So here, let's see, the integral of this would be 4/3, 3/4, I think. Okay, and then when you divide x, because this gets multiplied, so this divided by x is this, but with this constant, and so when you integrate it again, it becomes 4/3, but this would be, this constant would be squared. So the answer would be 3/4, 4/3 ln of x, minus this times, the integral of this times this, which is 9/16 x 4/3, I think. Comment if I'm wrong. Okay. So this one is a very evil one. If you're a math nerd, then you would know this. Thankfully, I know the Pascal's triangle, so I don't exactly memorize this, but because I've somewhat know what this is already because of the pattern. This is actually x minus 1 cubed and x plus 1 to the power of 4. If we do, so I'm going to let u equals x plus 1. I don't know why I thought of this. I should have thought of this earlier. The reason why I want to do x plus 1 is so that the monomial is in the denominator. Okay, if we have the monomial in here, but we have a polynomial in the denominator, it's going to be very nasty. So we're going to avoid that. Mainly because I hate doing tedious math. So 0, 1, this was, let's see, x plus 1 is u to the power of 4. So u equals x plus 1. If we let u, see x minus 1, see u is equal, u minus 1 is x. U minus 1 minus 1, that's u minus 2. So I have u minus 2 cubed on the top. Du. Okay. Holy jeez, this is nasty. I'm most likely gonna change these two as well, because it's gonna be a long polynomial. 1 to 0. Let's see. 1. If I plug in 1, it'll just be 2. So it'll just be 2 to 1. Just put it behind it like that. Okay, so now we're gonna have u cube. Oh god, if I could sort of try this. Let's see, that's 6 u squared plus what? 3 times 4? 12u minus 4? Oh no, not minus 4. I don't know why I put minus 4. Minus 8. Is that right? I think it's right. Looks right. Scientifically correct, I think. Okay, and then all divided by u divided by 4. So here, this is still an integral. Here we, oh my god, this is long. Oh god. If we simplify this into a polynomial instead of a nasty rational, we will get 1 over u minus 6 over u2 plus 12 and then 8 over u4. I should have written it in exponential, would have been much faster. Okay. So this is equal to, so this I know is ln of u. Okay. Here this one is plus, if you memorize the integral of 1 over u2, or I mean 1 over u square, the integral of 1 over u square is negative 1 over u. So the sign alternates. So this is 6 over u. Here, sign alternates as well. This is a u square. The integral of this is equal to negative 1 over u square. So this is, let's see, if I take 2 out, that's a 6. So the constant is 6. Here, I really don't know. Negative 8 u4. That is negative 3, 8 over 3? Because it's plus 1. I guess so. So positive 8 over 3. Or, yeah. That. Whatever. Okay, and then 2 to 1. So here, let me check this just in case. Let's see, 12 u negative 3, negative 2 just gives me negative 6. Okay, alright, so far so good. We're here. At this point, I would have lost. 2, if I plug into ln of 2, this is just ln of 2, plus 3 minus, oh god, why would you do this to me? 3 over 2, 8 over, let's see, 2 cubed is 8, so 8 over 24. 8 over 24, 8 over 24, what's 8 over 24? 1 over 3? Okay. So all that minus 0, 6 minus 6 is 0. Oh my god. 8 over 3. I swear to god, if all this cancels out. 6 over 2 minus 3 over 2 is equal. Wait, 6 over 2 minus 3 over 2. That's 3 over 2. Plus 1 over 3. So that's, so 3 halves plus 1 over 3. That's like 11 over 6. So 11 over 6 minus, let's see, 2, 8 times 2 is 16. Okay. That's negative 5 over 6. So the answer is ln of 2 minus 5 over 6. Oh my god. That's such a specific number. Okay. Let's move on. Okay, 0 to pi over, pi over 2 to 0. No, 0 to pi over 2. So here, so this sine x, cosine x, this trig identity is half of sine 2x. And this trig identity is cosine of 2x. Alright? This integral is just, let's see, sine that is negative cosine. So it would be negative 1, 4, because the inside of the constant divides. So negative cosine 2x plus a half of sine 2x, right? Yeah, okay. And what sucks about this is that this is a definite integral to 0. Oh my goodness. Okay, pi over 2. If we do pi over 2, let's see, that's cosine pi. Cosine pi is -1, so we'll have 1 over 4. And then this is sine of pi. Sine of pi is 0. Okay, we're done. Minus, and then if we plug in 0 here, plugging in 0 is, let's see, cosine of 0 is 1? Yeah. 1, so it's -4. Okay. This is, so the answer is just 1/2, I think. Okay. Cool. Next one, ln square. Alright. Ln square. So the ln square, I don't know why, oh, well, I guess I might as well, since I wrote the integral sign. Alright, so here, I'm gonna let u equals e to the x. Wrong order. X equals e to the u. Okay, so I'm gonna do this the physics way, because I hate integration by parts. So here, this is dx e to the u du. Okay, here's what happens. When I plug in e to the u, where x is, I get ln, well, here, let me write it like this. Okay, and that dx is e to the u du. What this does is this gives me u squared e to the u du. Okay, this is much easier because now I can just start panicking like this, and then e to the u, and then go like this. Okay, at this point I will just write it as e to the u times u square, right? It goes u square negative 2u and then 2 plus 2. And then you can go ahead and write your answer. E to the u is x. So this is, the answer is x times, let's see, u square. I pretty much let u equal ln of x. That's what u is. So this is ln of x square minus 2x ln of x plus 2x plus c. Yeah. Okay. Much better than actually doing the integration by parts, where you where you derived this and then integrate 1. Yeah, I don't like that. Okay, here, holy Jesus, 2x, negative 2x plus 1. This is 2, then we have 0. Now the reason why I don't want to do this is because now you have annoying constants. So now we have 1 over 9, 1 over 27, okay. So now you have a long answer, e to the 3x, and then you get, well, I guess I could do like that, then do x squared minus x minus 2x minus 1 divided by 3 plus 2 over 9. Yeah, I guess. Look how quick I did that. Wow. I don't know. Some competitions wouldn't allow this. They would want that simplified or in expressed, and it's annoying. Very annoying. Okay. Okay. So that made me hesitant a little bit, but then I'm starting to see this trick. So this is, if I take x out, this is 3 plus x, right? So this is, I can literally just separate that plus ln of 3 plus x. Okay, and if you're lazy like me, you can use this formula here. The integral of this is x ln of x minus x. So here, I'm going to go and do ln of x, or x ln of x minus x plus, I don't know, see if I let u equals that, I pretty much do ln of u. So it's going to be the same thing, x plus 3 ln of x plus 3 minus x plus 3. And then you can just simplify it however you want it to be. Yeah. Okay. So there you go. That's all the MIT 2007 qualifying integrals. Alright. Hopefully you learn some techniques. This was all improvised, so no, I did not solve this before. This is just all in one go. That's pretty much what I'm doing for probably the rest of the integrals. So, yeah. Well, some integrals like this, I would already know because I have been doing a lot of integrals. But after like a month break from doing integrals, it's a lot hard for me to detect what techniques to use because I'm sort of getting a little rusty. So thanks for bearing with me. So I'll see you guys in the next video. Thanks for watching, subscribe, and I'll see you guys next time.